Hello everyone, welcome back to the channel. Today we are going to be discussing the elastic properties of solids. We know what elasticity is, the ability of objects to return to their original size when an applied force has been removed. Well, I'm sure that you have textbooks to build on all those fundamentals, and maybe I'm going to make a different video for the theoretical knowledge. But let's go straight to the parts of elasticity that involves calculation. And Hooke's law said, provided we do not exceed the elastic limit of any material, the force is always going to be proportional to the extension you see. What that means is that if you see an elastic material like a spring and you apply a small force, it will extend by a small amount. And if you increase the force, the extension as well will increase, and they do so in proportional form. Such is the statement from Hooke's law. If the proportionality is converted into an equation, we have something like this: F equals Ke. The K stands for the spring constant, usually measured in Newton per meter. The SI unit is Newton per meter. E stands for the extension of the material due to the force, which is usually measured in meters. And F stands for the force applied, always measured in newtons. Now, besides this formula, there are lots of ratios that were bettered from this formula alone. If I was to make K subject of the formula, it means that the ratio of force and extension will always be constant, provided we are within the elastic range of that material. So this statement can be interpreted into different hybrid equations like this. We can say that the first force you applied over the extension it produced is always going to be equal to the second force you apply over the second extension it will produce. Now, this formula is useful when we are not asking you about the spring constant. We just want to know, when the force of this was applied, it extended by 2 cm. If a force of 5 is applied, what will be the extension? So when you're looking for a final extension when an initial extension was given to you, this is the perfect equation for it. So after this, already we know that every force is actually mass times gravity, is it not so? So the second force is also its mass times gravity. So what that means is that gravity is common. So if I slash out gravity, we can get the second ratio that says m1 over e1 is equal to m2 over e2. So these two equations work very well for finding initial and final extensions. Besides this, there are questions when you will be given the initial length of the spring, and then when you apply a force, it stretches to a certain length. So when you're looking for unstretched length or original length, we tweak these two formulas to look like this: F1 as well over the first extension minus the original, because that's how we get extension, the final length minus the original. This will be equal to the second force also into the length it gets to from the original. And you know very well that since these forces are simply mass times gravity, gravity can cancel both sides, and we can still write it like this: that m1 over the L1 minus L0 is also equal to m2 over the L2 minus L0. So an equation like this is very useful when you were provided with a very original length, or you're asked to find the original length. Then this becomes very handy. Then last but not the least, oftentimes, especially when we're dealing with springs, masses have what they call the mass hanger. So the mass hanger also has a mass, right? So if we use a mass hanger during the experiment, we can tell that this mass is 2 grams that we're adding on the hanger, but we probably can't tell what the mass of the hanger is. So when hanger is involved, you write the equation like this: that the mass you're bringing in plus that of the hanger all over the extension they produce, it will be equal to any second mass you bring in plus the same mass of that hanger all over extension 2. We're trying to say that when mass hanger is involved, both the mass and the hanger are responsible for the extension produced.